So first of all, I want to begin clearing up something that Nicholas asked about after class last time. So this is I think he's not here right now. So it was the following question. So what exactly is the Étale site? So there was some actual subtlety, which I kind of elided. So I claimed there was a morphism from the FPPF site to the Étale site. And Nicholas rightly pointed out that as I defined things, that's not actually strictly true. So what was this morphism? Well, let me remind you, a morphism is just a functor going the other way with some properties. So it's supposed to preserve fiber products and send covering families to covering families. But here, let me remind you, so this was Étale morphisms, which were locally finitely presented and Étale. So that was X schemes. So those were the objects of this category. And this was, the objects here were FPPF X schemes. So that's faithfully flat and finitely presented. So there's a difference between those two. Like there's not a natural functor going from right to the left, because if you have a locally finitely presented X scheme, it might not be finitely presented. Okay? Do you guys see the issue? I mean, this is some kind of very esoteric thing, but okay, you know, it's worth being careful. Okay, so what's actually the case is there's no morphism like this. So there's a morphism to a separate category to what I would call X Étale finitely presented, where here the objects are Étale X schemes, which are finitely presented, and covers are covers. Okay, and then there's a morphism like this. Okay, and this morphism over here induces an equivalence on the category of sheaves via push forward. Okay, so what that means is that there's a functor from sheaves on X, there's an adjoint pair of functors from sheaves on X Étale to sheaves on FPPF. So for all intents and purposes, we can treat these two sites as being the same thing, but it's worth being more precise. All right, are there questions about that before I move on with the sort of course material? If that felt extremely esoteric to you, don't worry. I mean, it's not going to be important in what comes next. Okay, so let me remind you what we talked about last time. So last time we were kind of developing analogs of like the usual properties of sheaves on topological spaces. So we constructed a notion of stalks. We discussed push forwards and skyscraper sheaves. We proved that sheafification exists, and then we used that to conclude that the category of sheaves is an abelian category. Okay, so with that, we actually have enough now to well, almost define a sheaf cohomology. So I owe you one more thing before we can make sense of sheaf cohomology for sheaves on the Étale site. So can anyone remind me what that is?
Enough injectives.
Yeah, enough injectives. So let's actually just prove that. So theorem. So this is going to be fairly easy with what we've already developed. So the category of sheaves on X Étale has enough injectives. Okay, so I'm curious actually, does anyone see the proof?
Are we putting any assumptions on X?
No.
Do you just grab the injectives from the inclusion maps on the sheaves? Or the restriction maps?
Can you say a little bit more about what you mean, Amelia?
I'm not sure.
Okay, that's all right. So what do we have to do? So we have to so given a sheaf F in the category of sheaves on the Étale side of a scheme X, we want some injective sheaf I with a monomorphism F into I. So here, this is sheaves of abelian groups. Sorry. All right. So we're actually just going to be able to copy well, at least one of the usual proofs for sheaves on a topological space. It'll be just like our construction of sheafification. So it's some analog of the Guatemala resolution. So what do we do? So for each x and x, so each point x and x, like in the literal topological space, we're going to choose a geometric point x bar mapping to x, mapping to big X. Okay, and I'm going to just let I of x bar be an injective module and an injective abelian group. With a map from the stock of f at x bar into I of x bar. So these exist just because the category of abelian groups has enough injectives. Does anyone remember, by the way, how to characterize injectives for in the category of abelian groups?
It's a sort of their extension principle for ideals in your ring, like Bayer's criterion.
So yeah, so for abelian groups, it's the ring is just Z. So there's a simple description. They're just injective, or sorry, they're just divisible abelian groups. Right. So that's the easy way to think about injectives for abelian groups. So like, for example, Q is injective or Q mod Z is injective. All right. So it's somehow, I mean, if you haven't seen this, you should try to figure out why there are enough injectives in a abelian group. So why does every abelian group embed in a divisible abelian group, and then why are divisible abelian groups injective? Okay, so now we're basically done. So now the claim is just that the product over x bar, so these geometric points we've picked, of the push forward, the skyscraper sheaf, located at x bar of these I of x bars works. Okay, and the proof, well, what do we have to do? We have to check two things. So one is that there's a monomorphism from F into IX bar. So can anyone tell me what that is and why it's a monomorphism? So maybe if you can tell me one of those two things, that would be fine. So what is the natural map from F to IX bar? Or sorry, it's not IX bar. So let me call this I. So there's a map from F to I. So it's the product of the skyscraper sheaves, which is IX bar at each geometric point X bar. Okay, so we're trying to map into a product, so it's enough to map into each of the components. So can anyone tell me how to map from F into one of these skyscraper sheaves? It's fine. Oh, people are writing in chat. I'm sorry, I missed that. Oh, and Sophia has been answering a lot of my questions in chat. Sorry, I missed that, Sophia. Okay, yeah. So let me just remind you. So F maps to the skyscraper sheaf, which is fx bar at x bar, and what's the map? Well, given a section, you just send it to its germ, right? Its value in the stock. And then the skyscraper sheaf associated to fx bar maps to the skyscraper sheaf associated to ix bar, because push forward is a functor. Okay, so that's the map. And then to check it's a monomorphism, so Peter answers correctly in chat, you just check on stocks. And last time we had a lemma that if you can check injectivity of a map of sheaves on stocks. Okay, so now we actually have everything we need to compute Étale cohomology, or to define Étale cohomology and give a formula for it. I wouldn't say it's exactly a computation. But before we do that, I just want to tell you a couple of other things that we've gotten out of all of our work in doing this. So in particular, what else can we get from sheafification and so on. Okay, so the main thing we've gotten now. So let me okay. So what have we achieved? The category of abelian sheaves on X Étale we now know is abelian with enough injectives. Okay, and before I move on, maybe it's worth remarking, and this is true for the category of abelian sheaves on any site. But it's substantially harder. All right.
It'd be obvious that the curly I is an injective sheaf.
Oh yeah, so that's 3. So you have to check it's injective. Good call. And I wouldn't say it's obvious, like it's something you have to prove, but the proof is exactly the same as for like the usual construction for sheaves on a topological space. So what do you have to check? You have to check some lifting property, and you should just check that by hand. The point is, it's very easy to map into this kind of sheaf. So you should try that, Irvin. Cool. Okay, so this is true for sheaves on any site. Okay, so before we move on to discussing cohomology, I just want to remark that we can also make one more construction, so we can define push forwards. Sorry, we've already done push forwards. We can define inverse image of sheaves. So again, this is something that makes sense for any morphism of sites, but we're just going to define it for morphisms of Étale sites coming from honest morphisms of schemes. What's the situation? So we have some map F from X to Y. So first of all, there's a functor induced on pre-sheaves. So here's the pre-sheaf version of inverse images. So this is a functor I'll call F inverse from pre-sheaves on Y Étale to pre-sheaves on X Étale. Okay, and what is it? So I'm going to define F inverse of a sheaf F. Well, so this is capital F is a sheaf on Y Étale, and I want to construct a sheaf on X Étale. So I need to say what it does on a Étale map V to X. And what it'll be is just the usual formula. It'll be the direct limit of F of U, where here, let me maybe write it this way, U to X, where here we have a diagram. So where the direct limit is taken over. Diagrams over the follow up like this. So we have V to U. This is Y, and this is X, and these are our maps. Okay. Okay. So I mean, you can make sense of this in general. So maybe let me say how you would make sense of this. So this construction makes sense for any morphism of sites. So what do you do? So you take the direct limit. So to evaluate on some V, you take the direct limit of, well, you look at your objects of your category, you apply the functor F inverse coming from this morphism of sites, and then you look at maps to F inverse of U. So this is a concrete way of describing that. Okay, and then the fact you should check, so the fact is that F inverse, so this functor on sheaves, is left adjoint to push forward. This is as functors on pre-sheaves. So here we have pre-sheaves Y Étale to pre-sheaves X Étale. Okay, and we have, this is F inverse and this is F star. Great. Okay, so now to define it on sheaves, so we know how to sheafify a pre-sheaf. So we define f upper star of f to be the sheaf associated to f inverse of f. I think I called that upper A. So okay, so the theorem is that f star is left adjoint to f lower star, just like in the usual topological situation. Can anyone tell me why this is true? It follows from the fact before and what the other things we've done. Any ideas?
Because harms of pre-sheaves are the same as harms of the sheafifications. Is that
Yeah, and I think what you're saying is right. So the point is that sheafification is a left adjoint. So it preserves left adjoints. Yeah. So Peter asks, should the morphism, yeah, and Sarah also said that. So Peter asks, should the morphism be from X to Y? Yeah, so the morphism is from X to Y. So that means pull back.
Yeah, I mean, in the diagram that you draw.
Oh, sorry about that. Yeah, you're right. Yeah, good catch. Thank you for pointing that out. Cool. Okay, so we have this inverse image, and just as an example, I mean, this is sort of transparent. If we have X bar including into X, this is a geometric point, then let's call this iota. Then iota star F is what we had before, the stalk. Okay, so this is not a really serious example. But I mean, we can do there. It's not so hard to make other examples. So this is maybe one example, but for example, let's suppose you have Y to X as any morphism, then the pullback of the constant sheaf Z mod LZ. So what is that? Can anyone tell me?
Isn't it still the constant sheaf?
Yeah, and that's a special case of the following general phenomenon. So suppose we have Y to XF, and then we have some sheaf F, which is Hom over X into some X scheme Z. So if we have a representable functor, so then what's F star of F? Can anyone tell me?
It's going to be Hom over Y instead.
So Hom over Y of what? Into what?
Going into the pullback of.
Yeah, so it'll be Y times Z over X. Okay, and this is something you can check, for example, using the adjointness or derive it from the definition if you so desire. Cool. Okay, so this previous example is the case where we took the representing object to be just X times the constant scheme Z mod LZ. Cool. Are there any questions about that? All right, I think in that case we've gotten what we can for now out of these sorts of constructions. So let's talk about Étale cohomology, the whole point of the course. So okay, so first of all, let's talk about how to compute Étale cohomology. So let me just remind you. So first of all, what's the definition? The definition is, so given an abelian sheaf, F in sheaves on the Étale side of X, we're going to just define HI, well, maybe let me write it this way, HI of X Étale F these are just defined to be the derived functors of global sections, meaning take sections on X of our sheaf F. Great. So that's the definition. Okay, so how do we compute this? Like how do you compute a derived functor? Yeah, you take an injective resolution. That's right. So thank you, Jose. So we choose an injective resolution. So that means F to some I0 to I1, where these are all injectives, injective objects. We now know that we can do that. So we just pick an inclusion of F into some injective sheaf using our theorem from before. Sarah says it's easy. I agree. Okay, and how do you do I1? Well, you take the quotient of I0 by F. That's some other sheaf. You embed that in an injective, and then you keep going. Okay, and then to compute, so that tells us that HI X Étale F is the same, and this is, you know, part of the theory of abelian categories with enough injectives, or the theory of derived functors. This is the same as HI of the following complex, so gamma of X I bullet. So here, what do? We've taken this complex of injectives, we've taken the global sections, that's a complex of abelian groups, and we take HI of that complex of abelian groups. Okay, so that's not, you know, not literally computable. You can't actually write down an injective resolution of most you know, most sheaves. I guess you can do it for the zero sheaf or something. Okay, but I just want to remark, I mean, we can also use this to compute derived functors in general, and we're going to use the properties of these things. So for example, suppose I want to compute Ri pi lower star of F, where here pi is some map, let's say, from X Étale to Y Étale, coming from a map of schemes. Like, this is also something we can compute. So what is it? It's HI of the following, of the complex of sheaves pi lower star I bullet. Right, so these are now sheaves on Y Étale. Okay, so any of the functors we've defined now we can actually compute their derived functors. So here implicit is the claim that pi lower star is left exact, and that's something I asserted in the past, and you should check. Okay, you could also, for example, take Li pi upper star of some sheaf G. Okay, but this actually is going to be 0 if I is bigger than 0.
So can I ask a quick question?
Yeah, go ahead.
It seems that above pi star of curly I dot should give an injective resolution for pi star of F, right? So don't you need?
Well, why is that?
Because otherwise, how do you define it as?
So pi lower star is not an exact functor, right?
Right.
So if you take if you apply, so I bullet is a sheaf which is exact away from degree 0, but when you apply a non-exact functor to an exact complex, it doesn't stay exact.
So you're not
so these are now sheaves.
Okay, but you're not saying that that's HI of pi lower star of F as a sheaf on Y.
That's correct. Yeah, this is the, maybe let me parenthesize this. Maybe that'll make it clearer. These are the derived functors of the push forward functor. Yeah. So the former is kind of a special case of the latter. If we're over an algebraically closed field, like taking cohomology of a sheaf, it's the same as we kind of discussed this last time. I think Sophia asked about it. It's the same as taking the derived functors of push forward to spec K if K is algebraically closed. All right. So here I claimed that, you know, so I've made a claim here about pullbacks. So the claim here, the implicit claim, which you should prove as an exercise, is that that pullback is actually an exact functor. Okay, and I think what ends up being the case is it's pretty easy to see that F inverse, pullback on pre-sheaves, is exact. And then the implicit claim here is actually that sheafification itself is exact. So sheafification is, I guess, right exact because it's because sheafification preserves co-limits, and then she's picking then checking left exactness of sheafification is something that I don't know how to do except by hand.
Can we show this by like maybe very existing a right adjoint to a left adjoint to pull back as well, or something like that?
You can, but actually constructing such a thing is not so trivial. And as far as I know, it doesn't exist in general. So it exists under some pretty broad special cases, but this exactness of pullback is true in general. Yeah, that's a good question.
Thank you.
Yeah, so we'll discuss that later in the course. I mean it's closely related to compactly supported cohomology. Okay. So what are the basic properties of sheaf cohomology? So basic properties. I'm just going to list these, although they're formal from the usual theory. Can you guys hear the blower right outside my window? Sophia asks, is it because filtered colimits are exact here? Yeah, that's right. That's a good, yeah. Okay, so what are the basic properties? So first of all, H0 of X étale F is just F evaluated at X. That's also known as the global sections on X of F. Basic property 2 is that if you take the cohomology of an injective object, it's 0 in positive degree and for I injective. Okay, and basic property number 3 is that there's a long exact sequence associated to a short exact sequence. Oh, Sarah, I'm glad you cannot hear the blower. It's quite loud. So given a short exact sequence of sheaves, so this is a short exact sequence in sheaves on X étale, we get a functorial long exact sequence. So hi minus 1 X étale F3 goes to hi X étale F1 goes to hi X étale F2 goes to hi X étale F3 and so on. Okay, and this just follows from the usual properties of derived functor cohomology, of derived functors or effaceable delta functors, or whatever your preferred formalism is. All right. Are there any questions about this? All right, so let's do an example. So let's consider the following case. So suppose K is a field. Then I want to consider the category of sheaves on spec K étale. So can anyone give me a description of this category of abelian sheaves? Hopefully the people in the window behind me are not too hypnotizing.